Are there any questions before we get going? Lecturing to a virtually empty room is interesting, but anyway, thank you for being here. Okay, we were talking about hypothesis testing. This is an incredibly important collection of ideas. Excuse me. The technique is not, what I think is most important for you guys to gather here. It's more the way of thinking about things, the way of thinking about making decisions based on data that have some uncertainty, that have some random component, that have some errors that aren't, can't let you perfectly tell the difference between two scenarios. So it just comes up over and over and over again in life that you are faced with a choice or a decision to make, and there's all kinds of mistakes that can happen, and they have different costs associated with them, different consequences associated with them. So the simplest setup is trying to decide between two visions of the world, two hypotheses about the world. We saw this kind of a thing in we saw this kind of a thing in the chapter on the Let's Make a Deal problem, the second chapter on that, where we were using data to try to decide between a scenario in which we were drawing from a box that had 50% ones and 50% zeros, and a scenario where we had 2/3 ones and 1/3 zeros. And we saw that there was two kinds of mistakes we could make depending on what the real situation was. If in reality you're drawing from the box with 50% ones, you could erroneously conclude that you're drawing from the other box, and vice versa. In hypothesis testing, we typically think of one of the hypotheses as being privileged. It's the null hypothesis. It's sort of situation normal, and we're trying to see whether situation is normal or something unusual is going on. The real restriction on what hypothesis to take as the null is that we are going to need to be able to compute the chance that our test rejects the null hypothesis when the null hypothesis is in fact true. That chance is called the significance level of the test. And so if our null hypothesis doesn't allow us to calculate that chance, we can't use this sort of hardware of statistical hypothesis testing. So under the null hypothesis, we need to be able to compute the chance that we will reject the null hypothesis. When I say under the hypothesis, what I mean is assume the hypothesis is true. What's the chance that my test then rejects that hypothesis? All right, so a type 1 error is rejecting the null hypothesis when the null hypothesis is true. A type 2 error is failing to reject the null hypothesis when the null hypothesis is false. Right? The chance that we fail to reject the null hypothesis when the null hypothesis is false is going to depend on the way in which it is false. Different scenarios under which it's false will lead to different probabilities of failing to reject the null hypothesis. So that second idea, the chance of making a type 2 error, failing to reject the null when the null is false, is going to depend on which particular alternative hypothesis is true. So we have the null hypothesis, and then we have one or more alternative hypotheses. Either the null is true or one of the alternative hypotheses is true. And typically when we compute the chance that we fail to reject the null hypothesis, that chance needs to be computed on the assumption that some particular alternative hypothesis is true. Sure. Sorry. All right, so let's look at, this comes up in law enforcement and the law, kind of generally. It comes up in all kinds of screening tests, so forth and so on, that the null hypothesis is somehow nothing is going on. The alternative hypothesis is something is going on, something in particular is going on. And in our legal system, the null hypothesis is that you're innocent because you're innocent until proven guilty, right? So it's sort of like you assume you're innocent, and then you need strong evidence, compelling evidence that you're in fact guilty before you should be found guilty by a court. All right, so let's look at this example of a speed trap. You're going down the street. There's a radar gun aimed at you. What's the null hypothesis in this situation? Is it that you're speeding or that you're not speeding? So the standard way to set this up would be the null hypothesis is that you're not speeding, and the radar detector is going to either give evidence that that hypothesis is false, in which case they would conclude that you are speeding and cite you, or not give evidence that the null hypothesis is false, in which case you wouldn't be cited, right? Okay, so the null hypothesis is that you're not speeding. What's a type 1 error? So type 1 error, remember, is rejecting the null when the null is true. Okay, yeah, it's B, yeah? Okay. So it's to give a ticket to somebody who wasn't speeding. Okay? And what's a type 2 error? Type 2 error is failing to reject the null when the null is in fact false. Okay, so that's rejecting the null here is to conclude that somebody is speeding. Failing to reject the null is not to conclude that somebody is speeding. And the null is false, it means they really are speeding. Okay, so a type 2 error here is to fail to ticket someone who was in fact speeding. Okay. This all make sense to everybody? Okay. All right. So we've talked about the two kinds of errors. A type 1 error is rejecting the null when the null is true. A type 2 error is failing to reject the null when the alternative is true, when the null is false. And significance level and power are related to the probabilities of making each of those kinds of errors. So the significance level of a hypothesis test is the chance that you reject the null when the null is in fact true, on the assumption that the null is in fact true. Now, you'll notice when you read this chapter that I sort of tried to use the subjunctive mood most of the time, like if the null be true rather than if the null is true, because B is sort of non-committal as to whether in fact in reality is true or not. It's like assume that it is and then what happens. So there's a lot of funny use of subjunctive mood. All right, so the significance level of a test is the chance that it erroneously rejects the null hypothesis. So assume the null is true. What's the chance that the test rejects it, even though it's true? The power of a hypothesis test is the probability of exactly the same event, but under a different set of assumptions. The power is the chance that you reject the null hypothesis, but not when the null is true, when a particular alternative is true. Okay, so in both cases, you're finding the chance that you reject the null, but the significance level is the chance you reject the null when the null is true. The power is the chance you reject the null when a particular alternative is true instead of the null. Okay, so two different probability distributions are involved. One is the probability distribution of what you see on the assumption that the null hypothesis is true. The other is the probability distribution of what you would see on the assumption that a particular alternative hypothesis is true. The event you're finding the probability of is the same event either way, the event that you reject the null. Okay, this sort of idea that it has to be a particular alternative hypothesis, well, sort of the general, thank you, the general null being false is not sort of strong enough to give you a particular probability distribution. You need to assume that some particular alternative hypothesis is true in order to nail down the probability distribution to do the computation with. All right, so ideally what we would like is a test that has very small significance level, very small probability of rejecting the null when the null is true, and very high power against all alternative hypotheses, a very high chance of rejecting the null when the alternative hypotheses are true. Okay, the problem is that there's a trade-off between significance level and power. For a given sample size, for a given way of collecting data, to drive down the significance level to have a small chance of rejecting the null when the null is true is going to typically end up resulting in small power. That is, a small chance of correctly rejecting the null when the null is false. So there's a trade-off between these two things. You can't simultaneously get small significance level and arbitrarily small significance level and arbitrarily high power. All right. Let's skip this example. I want to talk really briefly about p-values because these are something that you will see in practice. And the setup for them in a lot of the elementary books I'm not very happy with. So suppose that the way we test a hypothesis is we collect data, we calculate some statistic from the data, which we'll call a test statistic. And then if the test statistic is big, we're going to reject the null hypothesis. If the test statistic isn't big, we're not going to reject the null. So this is kind of like the let's make a deal problem where our test statistic was the number of times we won the game if we switched every time, played 50 times in a row. Okay? So we were going to reject the hypothesis that what's in the box was 50% ones and 50% zeros if we saw a large number, a sufficiently large number of wins by switching. Right? So if that value of the number of times you win by switching was sufficiently big, we'd reject the null. And if it wasn't, we wouldn't. Is that okay with everybody? We've got kind of the rhythm of this? All right. So x here is the thing we're looking at to decide whether to reject the null hypothesis. This is our statistic, the thing we're computing from data. We're comparing that to some threshold. And if we want the chance that we erroneously reject the null when the null is true to be small, then we would assume the null is true, and suppose we want to limit the chance that we incorrectly reject the null when the null is true to be at most p, then we would try to find the threshold so that if the null is true, the chance that that statistic is bigger than this threshold is no bigger than p. Okay? Now, if we have a rule that lets us sort of find that threshold for any value of p we want, we could call that threshold that depends on p x sub p. Right? So typically, how is xp going to vary with p if we have a setup like this? If we make p smaller, is xp going to get bigger or smaller? Let's just imagine plugging in 0 here, right? The chance that x is greater than or equal to 0, is that going to be bigger or smaller than the chance that x is greater than or equal to 5? Bigger, okay, right? It's the larger the value we put in here, the more restrictive the event, right? The fewer outcomes are going to be in there, and so the smaller the probability is going to be, right? So if we want to make this probability smaller, that's going to correspond to making this threshold bigger. Does that make sense to everybody? Okay, so in this setup, xp gets bigger as p gets smaller. Right? To have probability of rejecting the null smaller, we would take a bigger threshold, if this is how we're setting up the test. It's not the only way to do it, but it's what we're talking about here. Okay, so our test, our rule, would be reject the null hypothesis if the observed value of the statistic exceeds this threshold. So that's a test of the null hypothesis at significance level p, because the probability that x will exceed xp if the null hypothesis is true is no bigger than p. Okay, so the chance we erroneously reject the null if the null is true is no bigger than p, if we set things up this way. All right. So what is a p-value? Well, a p-value would be the smallest value of p for which we would reject the null in this setup. Okay, so normally the setup for hypothesis testing is you pick a significance level, like say 5%. I'm willing to have a 5% chance of incorrectly concluding that the null is false when the null is in fact true. Right? And I would collect my data, and I would apply the test, and I would either reject the hypothesis at significance level 5%, or I wouldn't. Okay? This is saying, well, instead of fixing that 5% ahead of time, I want to on the basis of the data, say, what's the smallest value of p for which I would have rejected the null hypothesis? So that might be some number smaller than 5%, bigger than 5%, whatever. But I say, okay, if I had tested at significance level 7%, I would have rejected the null. If I had tested at significance level 6%, I would have rejected the null. If I had tested at significance level 3%, I would have rejected the null. If I had tested any level less than 3%, I wouldn't have rejected the null. So then the p-value would be 3% in that scenario. Is this going to make sense? Right. By the way, how many of you looked at the chapter so far? Anybody? Nobody? Okay, the smaller the p-value is, the stronger the evidence against the null hypothesis. Small p-values mean that what you saw was really unlikely to happen if the null hypothesis was true. A very common misinterpretation of the p-value is to interpret it as meaning the probability that the null hypothesis is true. That's not what it is. We don't talk about the probability that hypotheses are true. We talk about the probability of data on the assumption that the hypothesis is true. Okay? This idea of a p-value, by the way, is the basis of the election auditing stuff that I was telling you guys about. So basically, the idea is you collect data. The null hypothesis is that the outcome of the contest is wrong, and you're looking for data to disprove that hypothesis. So you keep collecting data until there's very strong evidence that the outcome of the election must be correct. That is, that the null hypothesis that the outcome is wrong is really implausible. So we're computing the p-value of the hypothesis that the outcome of the contest is wrong, and we collect data until that p-value is really, really small, which lets us conclude that the null hypothesis is false. That is, the outcome of the contest is correct. Of course, there's still some chance that we made a mistake, because there's some chance that you get a value of the statistic that is really big, even if the null hypothesis is true. That's the chance of a type 1 error. That's the significance level, probability of rejecting the null when the null is true. Okay. Let's do an example, because this is all awfully abstract. Okay, let's, one of the common things to test a hypothesis about is the mean of a population. In this particular case, let's think of a 0-1 box, and we want to test a hypothesis about the mean of that 0-1 population. The mean of a 0-1 population is a percentage, right? It's the percentage of ones. So we have a population of 400 things. They're all 0 or 1. And I want to test the hypothesis that the fraction of ones in the box is 30% against the alternative hypothesis that it's bigger than 30%. I want to do that at significance level 5%, meaning I'm willing to have a 5% chance of concluding that it's bigger when it isn't bigger. And I want to do that on the basis of a sample of size 30 drawn from the population, simple random sample. And what I'm going to use as the test statistic, that x, that thing I'm going to calculate and compare to a threshold to make the decision, is the sum of the numbers on the tickets I get in those 30 draws without replacement, that simple random sample of size 30 drawn from the population. So under the scenario that we just mentioned, if the null hypothesis is true, then the number of tickets labeled 1 that I see in the sample has a hypergeometric distribution, right? It's the number of tickets labeled 1 you get in a fixed number of draws without replacement at random from a 0-1 box, okay? The number of things in the population is 400, that's big N. The sample size is 30, that's little n. And the number of good objects, the number of tickets labeled 1 in the box, is big N times that 0.3, 30%, which is 400 times 0.3 is 120. Okay? So there's 120 tickets labeled 1 in the box if the null hypothesis is true. Okay? So I want a test that will have power against the alternative I care about. And here, the alternative I care about is that P is bigger than 30%. That's just going into the problem. That's what you're being told is of interest, that the alternative is that P is bigger than 30%. So if I want to have a rule that has good power, that is, has a big probability of rejecting the null hypothesis when the alternative hypothesis is true, then for what values of the sample sum, the number of tickets in the sample labeled 1 that I get, am I going to want to reject the null hypothesis? Am I going to want to reject when x is big or when x is small? Bless you. It's written on the board in front of you, but yeah, it's right. If the alternative hypothesis is true, will I tend to see more ones in the sample than if the null is true, or fewer ones in the sample than if the null is true? More, right? The alternative is that there's more tickets labeled 1 in the box. Okay, so if I want a test that's sensible, that has a good chance of rejecting the null hypothesis when the alternative is true, then I should reject when the number of tickets in the sample gets big, right? So if I'm basing my test on how many tickets in the sample are labeled 1, what I'm going to use to construct the test, I'll find a threshold so that if the number of tickets in the sample labeled 1 is bigger than that threshold, I'll reject, because that's kind of more plausible if the alternative is true than if the null is true. So far, so good? All right, so yes?
So the 5% is saying it's like, that's 5% chance that it's the population or P is greater than 30%?
So the significance level is the chance that you reject the null hypothesis when the null hypothesis is in fact true. So we're going to design our test so that if P really is 30%, there's only a 5% chance we'll conclude that it's bigger. Okay, so it's our chance of making a mistake on the assumption that the null hypothesis is true. Okay, so we've got this random variable x, which is the number of ones in the sample. So in a simple random sample, I'll write SRS. Okay, it's coincidence that we've got 30% in n equals 30. That has no meaning, no particular importance. Okay, and what we know is that x will tend to be bigger if the alternative is true than if the null is true. Right? If the alternative is true that there's a larger than 30% ones in the box, then the number of ones in the sample is going to tend to be bigger than if there's only 30% ones in the box. Okay? So our rule is going to be reject if x is bigger than some threshold x alpha. Let me just call it x. No, x alpha. Okay, where we pick x alpha such that the probability that x is at least x alpha on the assumption that the null is true is less than or equal to alpha. Okay, in this case, alpha is 5%. So maybe I should just substitute 5% there so that I'll decrease some of the Greek. Okay. So I want to pick this number to be as small as possible, but yet keep the chance that x exceeds that threshold small. Yes? Pick x alpha such that, oh, x 0.05, sorry. Thanks. All right, so the x has some probability distribution if the null hypothesis is true, right? If the null hypothesis is true, then x is hypergeometric with parameters n equals 400, n equals 30, p equals 0.3. Yes? P equals 30%. Sorry, but G equals 120, I guess is the way we want to write this. Yes? Okay. So this tells me, this lets me calculate this probability for any value of x I want, right? And I want to pick x so that the chance, I want to pick this number so that it's not very likely that the sample sum would exceed that threshold if the null hypothesis is true. Then, if I see a value, if x turns out to be larger than that, I can reject the null hypothesis and feel pretty comfortable that I'm not making a mistake by rejecting the null hypothesis, because it's very unlikely that I would have seen such a big value of x if the null hypothesis were true. Does this kind of make sense? So how do we go about finding that number? So population size is 400. The number good in the population is 120. The sample size is 30. And I want to find the value here so that I want to find the smallest value I can so that the chance that x is bigger than that value is no bigger than 5%. This stuff is just all, it's hard to grasp. Like I know as I'm saying it that the sentences are complicated and it's kind of hard to get at what I'm saying. So why do I want to find, okay, does everybody understand why I want this chance to be small? Okay, this is the chance that I make a type 1 error. It's the significance level. It's the probability that I reject the null when the null is true. Okay? Why do I want to pick this value to be as small as possible while maintaining this? Suppose I made this be a million. Right? I'm drawing 30 times out of the box. The chance that the sample sum of 30 draws from the box is bigger than a million is going to be 0, right? Okay? So I have no to worry about. That's definitely less than 0.05. Am I ever going to reject the null hypothesis? No. That test would have no power, right? It would, even when the alternative is true, it would have 0 probability of rejecting the null hypothesis. Okay? What makes the power big? The smaller I set this threshold, the bigger the power is. Because the smaller I set this threshold, the greater the probability that I'll reject the null hypothesis when, in fact, p is bigger than 30%. Does that make sense? Okay, so to sketch this, I have more than one eraser. All right, so remember this. X tends to be bigger if the alternative is true than if the null is true. So we could try to just kind of sketch the scenario that here's, say, the probability histogram for x So this might be the probability histogram for x if the null hypothesis is true. If the null hypothesis is true, what's the expected value of x? Sorry? what's the expected value of a hypergeometric random variable? So it's n times what's the analog of p, right? Okay, and what? Okay, so we've got 30 times 0.3. Okay, which is something like 9. It's right there. How about that? 9. Okay. All right, so if the null hypothesis is true, we would expect to get 9 tickets labeled 1 in our sample. We're not going to get exactly 9 every time, right? It's a random sample. But the balance point of this distribution would be down here around 9, right? And if the alternative hypothesis is true, then let's suppose that instead of p being equal to 0.3, 30%, p is equal to 0.6, 60%. Okay? Then the test statistic, the number of tickets labeled 1 that we get when we reach the box and draw, would have a different probability histogram, right, under that scenario about the world. And the expected value of that random variable would be twice as big, be 18, if p were equal to 60% instead of 30%, right? Okay, so we're trying to find some threshold here so that if the null hypothesis is true, there's only a small probability juggling, not my strong suit. Yeah. Learning the slack line, though, that's fun. Okay, so that if the null hypothesis is true, there's only a small probability that we would see that many ones in the sample, right? But if the alternative hypothesis is true, there'd be a big probability that we'd see that many ones or more in the sample. Okay, so the power is, against this alternative that p is equal to 0.6 instead of 0.3, the power is, what's the chance that x is bigger than that if this is really its probability distribution? The significance level is, what's the chance that x is bigger than that if this is really its probability distribution? Okay? So again, it's the same event. In both cases, we're finding the probability that x exceeds this threshold. But to find the significance level, it's the chance that x exceeds this threshold if this is really the distribution. And for the power, it's the probability that x exceeds this threshold if this is the probability distribution. The alternative is true. Okay? So if we want to have a big chance of rejecting the null hypothesis when the alternative is true, we want to move this line down here. We want to set the threshold low. That gives us high power. But if we want to have only a small chance of rejecting the null hypothesis when the null is true, then we want to set the threshold big, right? So that there's only a small chance that we're out there. So what we want to do, if we're trying to control this probability of a type 1 error, control the significance level, we need to make sure that the area out to the right is no bigger than 5%. But having ensured that it's no bigger than 5%, we want to have it be as far to the left as possible because that gives the test more power. So we want to set the line as far to the left as we can and yet still have the chance that you belong beyond the threshold, be at most 5%, if the null hypothesis is true. Okay, so we're kind of sliding this around to find the place where this is less than 5%, but sort of as big as it can possibly be and still less than 5%. Okay, so that is move the line as far to the left as we can and yet have the probability be no bigger than 5%. So how can we find that number? We can do it by trial and error here. We want to find some threshold value, so the chance that x is bigger than or equal to that threshold is no bigger than 5%, right? But subject to that, we want this threshold to be as small as possible. So be pretty sure that the number we need is bigger than 9, right? Because 9 is the expected value, right? So let's start with a number like 11 for grins. Okay, at 11, the chance that we would reject the null would be 26%. So we haven't made it big enough yet, right? There's still a really big chance that we would be beyond the threshold. So let's try 15. Okay, 15 is now too big a threshold. There's only a 1.3% chance that we would reject the null. So that would be, that would satisfy this, but it's not as powerful a test as we can get, because if we move the threshold down, we might still be able to keep that chance below 5%, but yet have a bigger chance of rejecting the null when the alternative is true. So we're going to try moving it down a little bit and see whether we can still keep it below 5%. So let's see what happens with 14. Yep, it's still below 5%, right? So 13, it's no longer below 5%. So the smallest we can make it and have that number below 5% is 14. So if our test is reject the null hypothesis that there's 120 tickets labeled 1 in the box, if when we draw this simple random sample of size 30, we see 14 or more tickets labeled 1 in the sample, then that rule has a probability 3.4% of incorrectly rejecting the null hypothesis if the null hypothesis is true. As significance level, 3.4%. And this is the best we could do at 5% significance level as well. Because if we move this down from 14 to 13, then we have a bigger than 5% chance of rejecting the null when the null is true. All right, what's the power of this test against the alternative I mentioned, the alternative being that there's 60% ones in the box instead of 30% ones in the box. Right? My test is reject if x is greater than or equal to 14. What do I want to calculate to find the power against the alternative that there's 60% ones in the box instead of 30% ones in the box? So this is this threshold 13 now, right? And what we found is if this is the right distribution, if this is the truth, if there really are 30% ones in the box, then the chance that I'm at 14 or above, it's above 13, 14 or above. Oh, I'm sorry. Chance that I'm at 14 or above is 3 point something percent. Okay. And now what do I need to do to find the power? Finding the probability that the number of ones in the sample is 14 or bigger, but instead of it being on the assumption that there's 30% ones in the box, it's going to be on the assumption that there's 60% ones in the box. Okay, so I'm going to change the assumption about what's in the box, but I'm finding the probability of exactly the same thing. That is, the probability that the number of ones in the sample is 14 or bigger. Okay, so 60% ones in the box means that there's 240 good in the population, right? Twice as many. Okay, so what's the chance I reject the null hypothesis if this alternative hypothesis is true? It's the chance that I would get 14 or more ones in the sample if, in fact, there's 240 ones in the box. That chance is almost 96%. Okay? So this test would have significance level 5%. In fact, significance level a little smaller than that, 3.8 or whatever that number was. And the power against the particular alternative hypothesis that there's 60% ones in the box would be 95.8%. Okay? Significance level, chance you reject the null when the null is true. Power, chance you reject the null when the null is false. All right, chance you reject the null when a particular alternative is true. Okay? Yes?
So in this case, the test is good because it's low significance level of high power.
Well, it has high power. So the question is, in this case, the test is good because it has low significance and high power. It has high power against this alternative, that there's 60% ones in the box. But it's not going to have high power against, remember, the null is that there's 120. Sort of the alternative we care about is there's more than 120. It's not going to have very much power against the alternative that there's 121 ones in the box, right? If we look at that, then the chance that we would reject the null if there's just one more one in the box than the null says is not going to be very big. It's going to be really, really close to the significance level. Right? Does that make sense? So when we're computing the power, We're computing it under the assumption that a particular alternative is true. So this is the power under the alternative that there's 121 ones in the box instead of 120 ones in the box. And we can't get much power with a sample of this size. Okay? Yes? Yes. Power is 100% minus the chance of a type 2 error. So the question is power and the chance of a type 2 error related? So okay, so the power is the chance of rejecting the null hypothesis when a particular alternative hypothesis is true. Okay, so what's a type 2 error? Type 2 error is not rejecting the null when a particular alternative is true. So probability of A is equal to 1 minus the probability of A complement. Right? So the power, the chance of correctly rejecting the null when a particular alternative is true is 1 minus the chance of not rejecting the null when a particular alternative is true. Not rejecting the null when a particular alternative is true is a type 2 error. So this is 1 minus the chance of a type 2 error. So far, so good? Sort of? It'll make more sense when you read the chapter and start the homework. Or it won't. Okay. People heard of Zener cards? These became popular for testing ESP. They're cards that have geometric figures on them. There's 5 of them. There's a star, a square, a circle, some wavy lines, or a plus sign. And the idea was to have something simple and geometrical that someone could think about very hard and transmit the idea in their mind of what it is that they're thinking about to some other person, using telepathy. Okay, all right. So we're going to talk about a couple of tests of paranormal things in the class. This is one of them. The other is testing dowsing, using the forked stick to look for water or something like that. Okay, so we're going to set up an experiment for testing whether somebody has ESP. And what we're going to do is we're going to shuffle a deck of 5 Zener cards, and the psychic is supposed to figure out what order the cards are in, okay, without looking, right, without being told. So we need some rules of the game in order to figure out probabilities. We're going to shuffle them in such a way that every one of the 5 factorial permutations of the deck is equally likely, right? So 5 factorial is 120, I think. And so every one of those 120 orderings is equally likely. What are the rules? The psychic does not get told the answer nor whether she was right in any particular case until you've gone through all 5 cards. Okay, because otherwise that would be extra information. Like if I guessed that the first card was the plus card and you said, no, it isn't the plus, then it was in fact the wavy lines. Then I would know that the second card wasn't the wavy lines and was sort of more likely to be, okay, so I don't want to give that information away. So that's why we have this rule. We don't look at what the psychic wrote down until we've gone through the whole deck. That's, so our facial expressions or whatever don't, betray what's, okay. And the psychic has to basically pick a permutation of the deck. So that is, the psychic can't say plus all 5 times, right? Psychic has to say plus once, wavy lines once, circle once, square, okay? So, okay. All right. Okay, so what would, the null hypothesis is that the psychic doesn't do any better than just sort of random guessing, right? That it just sort of, the psychic's particular ordering of the deck, the guesses of the order, that they might as well just be some fixed permutation of the deck, and we're comparing that with a random permutation of the deck that comes from shuffling. There's sort of no connection between the two, right? There's no real psychic ability. So what is a reasonable test statistic to use to figure out whether the psychic has ESP, whether the psychic can figure out what order the deck is in? But if the psychic, what's the chance the psychic gets all 5 cards in the right order? 1 over 5 factorial, right? Because all 5 factorial equally likely. Okay, so to get sort of 5 matches, to get a perfect score, the chance of that by blind luck is 1 over 120, right? A little less than 1%. Whatever that is, like 0.8% or something like that, okay? If we didn't want to insist on a perfect match for everything, what would a reasonable test statistic be? How many she got right? How many he or she got right? Is that okay? So how many cards were guessed to be in the right place? And the maximum value of that is 5, and the minimum value of that is 0, right? Okay. Is 4 a possible value? Right. Okay. So if you get 4 of them right, the 5th only has 1 place to go, right? So you can't. 4 is not a possible value for the number of hits. Okay. 3 is a possible value because you get 3 in the right place and then swap the other 2. Right? So if we're going to use as our test statistic the number of hits, the number of cards that were guessed to be in the right place, the place that they really were, then we want to reject. What's the null hypothesis here? Null hypothesis is something about the psychic's ability, that the psychic has no psychic ability, that the psychic ain't. Yeah, okay. All right, so, and then if the psychic does have ability, we would expect more hits than if the psychic doesn't have ability, right? So we would want to reject the null hypothesis if the number of hits the psychic gets is surprisingly large on the assumption that the psychic actually doesn't have any ability. Does that make sense? So we pick our threshold for how surprising is surprising. And that's the significance level. Okay? So if we pick it to be 5%, then we would say, gee, if random guessing would only lead to this many hits or more 5% of the time, then if we reject the null hypothesis that the psychic has no ability when we see that many hits or more, we'd only have a 5% chance of concluding that the psychic has ability if in fact she doesn't. That make sense? Okay. So in order to do that, in order to pick the threshold, we need to know the probability distribution of the number of hits under the assumption that the null hypothesis is true. Okay, now here's where you can see that there's a really big asymmetry between the null hypothesis and the alternative hypothesis. If the null hypothesis is true, we know what the probability distribution is of the number of hits. We can figure it out, right? Because it's just, you take some particular fixed permutation of the deck. Now you shuffle the deck randomly and you look at how many of the cards ended up in the same place. You do it over and over and over again. Each time you count how many cards matched, how many hits there were. You can find the probability distribution for the number of hits if there's no psychic ability. Now suppose there is psychic ability. What's the probability distribution of the number of matches? You have to be a psychic. I mean, right? So in order to do a hypothesis test, we need to be able to compute the probability distribution. We need to be able to compute the probability that we reject the null when the null is true. In this case, if the null is that the psychic has no ability, we know the probability distribution of everything because it just comes from the shuffling of the deck. So that's something where if we label that as the null, we can compute the probabilities we want. If we label the null as the psychic has ability and we're trying to refute that, we're looking at rejecting the null hypothesis that the psychic has ability, well, how can we find the probability distribution of the number of hits on the assumption that the psychic has ability? We don't really know what that means, right? So we couldn't compute that, and we wouldn't be able to put it into the hypothesis testing framework in the same way. All right, so all right, let's do this question, because this is actually a little probability exercise we might be able to do in our head. If we make one pass through the deck, you would expect the psychic to get some cards right, even if the psychic has no ability, right? On the assumption that the psychic has no ability, how many cards would you expect him or her to get right? What's the chance that the first card is the square? 1 out of 5, right? What's the chance the second card is the square? It's 1 out of 5, right? What's the chance the second card is the wavy lines? 1 out of 5, right? The chance that any particular card shows up in any particular place is 1 out of 5. So the chance that any particular card matches what the psychic guessed in that place is 1 out of 5, right? Now, the events are dependent, right? Because if the square is in the first place, it's not in the second place, so forth and so on. But if we're trying to find the expected value, if we think about the event that the guess matches the truth in a particular place, okay? The indicator of that event, that's the indicator function, remember, is 1 if the event happens and 0 if not. What's the expected value of that indicator function? It's a fifth, right? It's just the probability that it's equal to 1, which is a fifth, right? It's 0 times the probability they don't match plus 1 times the probability they do match, which is 0 times 4/5 plus 1 times 1/5, so it's a fifth. Now, the number that get matched is the sum of the indicators for the 5 places, right? Those things there's the same probability of a match in each of the 5 places. So we have the sum, the expected value, the sum of 5 things. What's the expected value of a sum? It's the sum of the expected values. Each of these expected values is a fifth. We have the sum of 5 things, each of which is a fifth. Okay? All right. Okay, so now what's the probability distribution of the number of cards the psychic gets right in a single pass to the deck under the assumption that the psychic doesn't have ESP? I think there's a missing thing here, which is complicated. Okay, it's none of the above, right? It's not anything we know a name for. Okay? Here it is numerically, right? The chance that you don't get anything right turns out to be 44. There's 44 permutations that don't leave anything in its original place, right? So that you don't end up with anything right. So the chance of that is 44 over 5 factorial. There's only one way to get all 5 where they ought to be that has chance 1 over 120. There's no ways to get 4 where they ought to be, exactly 4 where they ought to be, and not the 5th, right? So that's not here. Now, if you want to see where this comes from, it's worked out in excruciating detail. Okay. All right. So let's suppose that our rule is we're going to conclude that the psychic really has ability if she gets 3 or more hits, 3 or more cards in the right place. Okay? What would the significance level of that test be? It's the probability that she gets 3 or more in the right place if the null hypothesis is true. Right? That's okay. And the probability of getting 3 or more is the probability of getting 3 plus the probability of getting 5. So it's a 12th plus 120th. Sorry? Yeah, 11 over 120. Yeah. So just slightly less than 10%. Right? So, okay. Okay, so here, that's not a, we almost need her to get do a perfect job on a single pass to the deck to have very strong evidence that she has psychic ability. So how could we get more power out of this test. Okay, so that if she, if it changes the odds a little bit, if she has a little bit of ability, we'd have a bigger chance of noticing. Well, one way to do it is to go through the deck more than once instead of just going through the deck once. Collect more data, right? And we can keep the significance level low and have higher power as well. So let's suppose that we go through the deck 3 times, all right? And we're going to reject the null hypothesis if she gets 9 or more hits. What's the significance level of that test? How do we go about doing that? Okay, so yeah, all the ways that she can get 9 or more on 3 passes through. The passes through the deck are independent, right? We're shuffling each time. Yep. So one way that she could get 9 or more would be to get 5 on the first pass, 3 on the second pass, and 1 on the third pass, yes? Or she could get 5, 5, and 5, right? That would be 9 or more as well. Or instead of getting 5, 3, and 1, she could get 1, 3, and 5, right? Same numbers in a different order. Okay, so we'd have to add up, we'd have to enumerate all the different ways there are of getting 9 or more in 3 goes. We would use the independence of the passes through the deck, right? The independence of the 3 trials, and figure out what's the probability that the sum is 9 or bigger. Okay? All right. So far, the test that we were looking at for the fraction of ones in a 0-1 box, where we were talking about 120 ones in a box of 400 tickets and pulling a simple random sample, et cetera, we were comparing. Our null hypothesis was that the parameter was equal, the parameter p, the fraction of ones in the box, was equal to 0.3, 30%. And the alternative was that it was bigger than 30%. Right? And it made sense under those circumstances to say, okay, our test is going to reject the null if we see a lot of tickets labeled 1 in the sample. Because that would have power against that alternative. Because under the alternative, we'd be more likely to see more tickets labeled 1 in the sample. Right? That's called a one-sided alternative. The alternative is that that value of that parameter is on one side of the null. Okay? A two-sided alternative would be the null is that p is equal to 0.3. The alternative is that it isn't 0.3. Right? Might be smaller than 0.3, might be bigger than 0.3. Right? If we want to have power against that alternative, instead of rejecting only if we see a lot of tickets labeled 1, we would also want to reject if we see too few tickets labeled 1. Right? Because if in particular one of the alternatives, one element of the alternative is true, namely that p is equal to 0.1 instead of 0.3, then we'd be likely to see very few tickets labeled 1. And we'd like to be sensitive to that as well. Okay? So if we want our test to be sensitive to to all the alternatives, right, then we need to have power against all the alternatives. Then we sort of want to make sure that what we're likely to see if the null is true, how do I say this differently? We're trying to set up our test so that the value of the test statistic, there's a big probability that we don't reject if the null is true, and there's as big a possible probability that we do reject if any of the alternatives is false, any of the alternatives is true instead of the null. So if our null is that our parameter is this, and the alternative is that it's bigger than that, and the probability distribution of the data tends to be bigger the parameter is, then we would reject if we see values beyond some threshold, because those values would be more likely if the alternative is true than if the null is true. Okay? But if our null is that this is true and our alternative is that it could be on either side, then if an alternative down here is true, we're more likely to see values down here. If an alternative up here is true, we're more likely to see values up here. So instead of rejecting just when we're bigger than some threshold, that's going to have terrible power if the truth happens to be down here, right? Similarly, if we only rejected if the values were small, that's going to have terrible power if the truth happens to be up here. So if our alternative is simply the parameter is different from this null value, then we would do a two-sided test to reject either if we see too many tickets labeled 1 or if we see too few tickets labeled 1. Right? You know, we want things to have good power against all the alternatives, so we want to maximize that. All right, so yes. Right, yeah. So if the alternative you're interested in is either because you can rule out small probabilities on some other grounds or because what's interesting is a departure in one direction, then you would use a one-sided test. So here's an example. I want to test the hypothesis that a coin is fair against the alternative that it isn't fair. All right. Is the alternative a one-sided alternative or a two-sided alternative? Coin is fair means probability of heads is half, right? Not fair could be probability of heads is bigger than a half or probability of heads is smaller than a half. Yes? Okay. I'm going to base the test on, the number of times the coin lands heads in some number n of tosses, and I want to test at 10% significance level. So if I want to have good power against the possibility that the coin has a small chance of landing heads, and also have good power against the possibility that the coin has too big a chance of landing heads, then I would want to design my test so that I reject if I see too few heads or too many heads in n tosses. Right? Okay. So suppose that I'm going to use 30 tosses, where should I pick my cut points to be? Where should the threshold be so that if I see fewer heads than that, I'm going to reject, or if I see more heads than this other value, I'm going to reject? Well, what's the probability distribution of the number of heads in 30 tosses if the null hypothesis is true? Whoops, try to make this vaguely symmetric. All right. So if the null hypothesis is true and I have 30 independent tosses of a fair coin, what's the probability distribution of the number of heads? Sorry? 15 would be in the middle. Does this distribution have a name? Be binomial? Yep. So binomial with n equal 30 and p equal a half if the null hypothesis is true, right? Okay. So what I want to do is find some threshold here and some threshold here so that the chance that I'm below or above adds up to no more than 10%, right? Because I want the significance level to be 10%. So that would mean that the chance that the number of heads falls outside that range, if the null hypothesis is true, is no bigger than 10%. So if I reject, if I see too many or too few, the chance that I would reject if the null hypothesis is true is no bigger than 10%. Okay? So how do I find that number? Go back up here to the calculator. So let's suppose we have a binomial. Oh, this is only set for hypergeometric. Try again. Oh, give you the tools you need to solve the problem. Okay, so we've got a binomial with n equals 30 and p equals 50%. And we want to try to pick values so that the chance that we're outside this range is no bigger than 10%. We want to make the range as narrow as possible, right? So that we have a good chance of rejecting the null when the alternative is true. But we don't want it so narrow that the chance we reject the null is bigger than 10%. Okay? So instead of, since this lets me select a range and find the probability that I'm inside the range, I want to find a symmetric range around 15 so that the probability of that range is no smaller than 90%, right? Okay, the narrowest thing I can, so that, but it's no smaller than 90%. So what happens if we start with something like, I don't know, how about 9.5? And what's the symmetric thing on the other side, like 20.5? Okay, so that's a symmetric range around the expected value, around what we would expect to happen, and the probability is 95.7%. So I can afford to come in a little bit, right? Maybe. I can afford to come in a little bit, provided that doesn't drop this below 90. So the question is it going to? And I think it probably will. We can check that easily enough by just adding one endpoint. $92, yeah, 21. Oops, other way around, 19. Up. Okay, so if we want one more, it's very clear that it'd be below 90%, right? So if I set my test to say I'm going to reject the hypothesis that the coin is fair if I see 10 or fewer heads or 20 or more heads in 30 tosses, then the chance that I will erroneously conclude that the coin is biased when the coin is fair is at most 10%. Okay? So the significance level of that test would be 9.9%. Now we could ask, what's the power of that test against the alternative that the coin really only has a 30% chance of heads? How would I use this to find that? What's the event I'm trying to find the probability of? The event that I reject the null, right? When do I reject the null? I reject the null if I see too few heads or too many heads. It's the same event. But if the alternative that the chance of heads is 30% is true, then the probability distribution is different. The event's the same, the probability distribution is different. Okay? So in that case, that's what the probability distribution would be. And what's the chance that I would reject the null? Well, the chance that I don't reject is the chance that I'm in that range from 11 to whatever that was, 19. Yep, 11 to 19. Okay. So the chance that I do reject the null is 100% minus this, right? Just like before, the chance that I would reject the null was 100% minus 90.1. The chance I would reject it is 100% minus 27. So I would have a 73% power against the alternative hypothesis that the chance that this coin lands heads is 30%. Does that make sense to everybody? Chance of rejecting the null when that particular alternative is true. All right. Timed out my connection? No. Yeah, I just said, suppose that in reality it was 30%, how likely would we be to reject the null hypothesis? Okay. All right. So let's look a little further. Suppose that I wanted to have 50% power against the alternative hypothesis that the chance of heads is 45% and the chance of heads is 55%. Okay, so what power does the test currently have against the alternative that the chance of heads is 45%? Okay. The chance I would be in this range is 85%, so the power is about 15%, right? There wouldn't be a very big chance that I would notice that the coin was biased by this small amount using this test. That make sense? So suppose that I want to have a test that will keep the significance level at 10%, but have a bigger chance, bigger than 15%, 50% chance of rejecting the null hypothesis if, in fact, the coin has a 45% chance of landing heads. What would I need to do? How do I make the power bigger and keep the significance level the same? Increase n, right? I need to toss the coin more times. Yes? Okay. So there's going to be a trial and error thing going on here, right? To kind of figure out how big the sample needs to be so that when I then set the threshold to have the right significance level, I end up having power 50%. Okay? So shall we start by, let's just start, do you want to do this trial and error experiment together to get the rhythm of it? Because I think there's something like it on the homework. All right, suppose that we toss the coin 60 times instead of 30 times. Now we have to figure out what's the test. Okay, we figure out the test on the assumption that the null hypothesis is true. So we've gone back to 50% here. And we want to pick a range so that the chance that we're outside that range is not bigger than 10%, right? So looks like, if we go maybe roughly, 23 or so and 37 or something like that. Just to ballpark it to get started. Okay, so I didn't quite pick a symmetric interval. What's that probability turn out to be? 92%. Let's see if I make this 36.5, whether... Okay, we're not going to be able to make it any narrower than that, right? And still have 10%. So our test would be reject if we see 23 or fewer heads or 37 or more heads, right? And that would give us significance level 9.2%. Now what happens if the alternative is true? That's going to tell us the power. So 45%, this is got an 80% chance of falling in the range. So all we've done is we've increased the power from 15% to about 20%, 15% to 19%. Okay, so we need a bigger n than this in order to get there. Right? We still don't have as much power as we want. So what happens if we, say, double this again? 120. We're going to go back to the null hypothesis where this is 50% to figure out what our test is. So what do you think? Start around 50 or so, see what happens. And go up to about 70. Okay, again, I haven't quite matched that. All right, that's symmetric at least, 91%. Can we go, you think we can go a little further? 51. Nope. Okay, so that's rejecting for the most possible values we can, and yet still keeping the significance level below 10%. Right? There's an 8.2% chance we would reject the null if we conclude that the coin is biased if we see 50 or fewer heads or 70 or more heads. Okay. Now, what's the power against the alternative that the coin is biased and has a 45% chance of landing heads. Well, we're finding the probability of the same event, but under a different assumption. So now we've got the power up to about 26 point something percent. It's still not as high as we want it, right? So you get the rhythm of this. We just keep increasing n, keep trying this until we find a place where when we set up our test to have the right significance level, the power ends up being 50% or bigger. Okay? Yes? That on the assumption that this alternative is true, the chance we would reject the null hypothesis is 50% or bigger. Yeah. Okay. Yes? Under the alternative hypothesis, it's not quite symmetric. Under the null hypothesis, it is symmetric because it has p equal to 50%. The alternative hypothesis is that it's 45%, and another alternative we're considering is 55%. It's going to be just the mirror image. Okay. All right. Okay. We've got about 5 minutes left, not quite. There's a case study in here. This came out of an employment discrimination case that I worked on ages ago, where somebody was claiming that people were being preferentially fired based on their age and ethnicity. And so there were some data collected, and there's very often statistical arguments made in cases like this. And so you can look at the involuntary terminations. That's basically being fired. Other is you leave voluntarily. You retire. Something else happens, and then kind of the total. And you could ask, okay, how can I test the hypothesis that there was discrimination happening? Right. So just like with the Zener card example, you can imagine that if people's abilities, if the reasons that people get fired have sort of nothing to do with their age, ethnicity, so forth and so on, you could model that as saying that it's as if you take a random sample of your employees of a given size, a random sample of a given size of your employees, and fire them, right? You're just blind to anything, utterly just firing people at random. Now, presumably that's not how companies operate, right? Presumably you get fired for cause, right? And the causes might not be sort of evenly distributed across all ethnicities, genders, ages, et cetera, because you're firing a particular person for a particular reason, right? Okay, all right. But if it turned out that the disparity across these age groups, genders, ethnicities, et cetera, that the disparity in the rates at which people were fired would be expected to be that large, even if you were picking people at random to fire without regard for anything, right? If it wouldn't be surprising under that circumstance, then these data would not be very strong evidence that there was discrimination. Does that make sense? Okay, just from the luck of the draw, you would see some differences in the rates at which people were being fired across these different demographic groups. All right? You would expect to see that even if nothing was going on. And by nothing going on, a model of that is you pick people at random to fire. So here are a number of different ways of slicing these data. One is comparing a particular subgroup to the rest of the ethnic groups. One is comparing male and female. One is comparing all of the ethnic groups to each other. One is comparing things based on age. You can split it a bunch of different ways. So if you look at these things, right, then they're not all evenly distributed. There aren't the same number of people in each of these categories in the first place. But you could ask, okay, suppose I just pulled random samples of people. They're labeled however they're labeled, right? I have people labeled by their age, their gender, their ethnicity, so forth and so on. I pull a random sample from the whole set of employees and say, you're fired, okay? how often would I see disparities like I see in this table, or even bigger disparities among the rates in the different groups? And the answer is, it turns out you would see it quite a lot, right? So these are p-values for these hypotheses. So if you just look at gender alone, the chance you would see such a big difference in the rate at which men and women were being fired is 82%, right? So that's not very surprising that you would see that big a difference, even if people were being fired at random. The chance that you would see that big a difference in the rates at which people were being fired based on being under 40 or over 40 is also something like 80%. Not surprising, even if nothing is going on. So for all of these, there's very large probability that you would see the disparities that you saw in the data, even if people were basically being fired at random, blind to everything, including their ability and job skills, right? Including their performance, just utterly blind to everything. So these data do not provide very strong evidence that there was discrimination. That make sense? Okay, so, all right, have a wonderful Thanksgiving, and I'll see you guys on Tuesday.